about the logic effort of the transmission gate. So here is example. So see here, first stage is an inverter, and then after the inverter, you have a transmission gate and the output. So the first question is, so we are going to calculate the logic effort and parasitic delay of this circuit. Yeah, my first question is, how many stages do we have in the box in this compound gate? We call it compound because it's not a single stage of the inverter. It has a transmission gate. How many stages we have here? Is it just one stage or we have two stages now? That's the first question. But before you answer this, you need to figure out how to define the stage. Like, what is a stage? Like, I guess I explained this before. Like, for one stage, like the current can only flow within one stage. Say before this stage, say we have another stage that is just an inverter. So inverter connect to this stage. So if you look at the current flow, the current can only flow start from the VDD. If it's the inverter, it will pass through this transmission gate and go to the input of the second stage. And the input of second stage is gate. Like current cannot flow into the gate. It can only charge the input capacitor here, and then this current stops. Like it can only discharge in this way. It cannot pass into the next stage. That's why we call this is a first stage because current stops here. And for the second stage, like this compound gate, you can determine whether it's a one stage or two stages. Because of the current also goes from the VDD, but it can pass through the source of the transmission gate and go to the drain of that. And then go to the output, as the output is the capacitor. It's kind of the current can flow within the whole compound gate. So this is only one stage. So even you have the transmission gate, you still regard everything as one stage. So what is the transmission gate? So basically when transmission gate is off, it's open circuit, it's nothing there, it's open. But if it is on, it's just two transistors in parallel. So say if it is on, in this case is there are two sides of two, in this particular example, two sides of two, one side of two NMOS and one side of two PMOS. So when they are on, the equivalent circuit is just the two resistors in parallel. These two are equivalent. So why do we use the NMOS and PMOS in parallel? I guess that's a kind of the question also for group number 3. So I got initially, I guess 2 weeks ago, we learned the kind of circuits like use a single NMOS as a NAND gate, as an AND gate. Say use an single NMOS, say if the gate is VDD, if the input is also VDD. So what will the output voltage be if it's initially 0? So at the end, it can only be charged to VDD minus VTH, because when the output is VDD minus VTH, the VGS is the VTH is in cutoff region, so no more current can flow through this NMOS. So the output can only stay at the VDD minus VTH. So if you use the NMOS to discharge, say the input is ground, and the other node of the is VDD, like initial condition across the capacitor is VDD. At the end, what will the voltage across the capacitor be? It can be 0, because in this case, here is the drain, here is the source. The drain source is always VDD. Sorry, the gate source is always VDD, so it's always on until the drain source equal to 0. So at the end, the output can be 0 volt. So it's kind of for this NMOS, like if you want it to pull up, it can only pull up to VDD minus VTH. But if you use NMOS to pull down, it can be 0. It can make the input output to be the same. So we call that NMOS pulling up is weak, but NMOS pulling down is strong. Strong, we can also say it's a normal condition. Like it should be strong, but like when you use it to pull up, it's weak. For the PMOS, it's kind of opposite. Say you have a PMOS. If one node of the input is VDD, and the output is the voltage across it if the initially is at 0. So what will the final voltage of the capacitor be? That will be VDD at the end. Because here is the source, here is the gate. The gate source is always VDD. So this PMOS is always on, so that keep charging the output until drain source to be equal. So you see, like if you use PMOS to pull up, like because you are putting the other node to be high as well. So it can make the input output to be the same. So we say like PMOS pulling up is strong. But if you use PMOS to pull down, what happens is here is 0. The other is VDD. So what happens is what will the final voltage of the capacitor be? So here, this side is a source. This side is the drain. So gate source is here. So basically, gate source is kind of keep decreasing until the output to be VTH, so that this PMOS is in cutoff region. So at the end, the output can only be VTH. It cannot be 0. So that we say like PMOS pulling down is weak because it cannot pull the other node to be 0. Like it can only leave an offset, leave the VTH to be there. So if you look at these two together, like PMOS is good at pulling up, NMOS is good at pulling down. So if you combine them together, like make them work as a parallel circuits, and then they will be both good at pulling up and pulling down. So that's why we use transmission gate like NMOS, PMOS in parallel. So they work like complementary for the pulling strength. But how can we quantify this kind of strong and weak so that we can use resistance? Because when we talk about the driving strength, it's kind of the resistance of the internal resistance of the transistor. So if it is strong, it means it has a smaller resistor. If it's weak, it means it has a larger resistance, so that the last current can go through that is weak. So okay, so normally, like if the K ratio, that is the mobility between the NMOS and PMOS, if it is 2, we would say like the equivalent resistance of NMOS should be equal to the resistance of the NMOS when it is pulling down, because pulling down of the NMOS is when it's strong. So that's a normal condition. But that resistance should be smaller than the pull up, because NMOS pulling up is weak, so that the resistance of pulling up should be high. Normally we say it's half of the, equal to half of the n pulling up. Similarly, for PMOS, it's the same idea, like equivalent P is equal to equivalent P for pulling up, because PMOS is good at pulling up. So that's the normal condition of the resistance of the PMOS. And pulling down is a weaker. So the resistance is twice of what it should be. So it's equal to half of the P pulling down. So we can move the factor half in front of those two, and use this. Similar for the other case. Multiply them by 2 together. So here's the resistance when it's pulling up and pulling down. So now let's look at our original circuit. So that is this one. Here's 4, here's 2, and you have a transmission gate. There are 2 and 2. Right, so now we're going to calculate the logic effort and parasitic delay of the circuit. So let's just take the pulling up as an example. So let's see, G up, the logic effort of pulling up. So when it's pulling up, what does it mean is here, the PMOS is on, so that there's a current flow in this direction, and it passes through this transmission gate and going to the output. So the equivalent circuits is something like it only passes this and passes this to transmission gate. If you remember how to calculate the logic effort, that is, first is look at find the reference inverter that has the same driving strength as the gate. So now, if you want to find the logic effort, first we need to evaluate the driving strength of the circuit. So driving strength can also be regarded as the kind of the resistance in the path. So basically here, first it passes through this PMOS. It has the internal resistance of the PMOS, and then it has 2 resistance in parallel of the transmission gate, and then go to the ground. So that is the total resistance in the path. So now let's look at the value of them. So first is size of 4 PMOS. So now we have both NMOS, PMOS, so we can normalize everything to be NMOS. Like the size of 4 PMOS, the driving strength of size of 4 PMOS is equivalent to size of 2 NMOS. So we can regard this size of 4 PMOS as size of 2 NMOS. So size of 2 NMOS, the resistance of the size of 2 NMOS should be 1/2 R equivalent N. So that's the first resistance of this PMOS. And then you have this this transmission gate. So for the transmission gate, it's kind of different. So because here you use the transmission gate to pull up, so which means this PMOS works normally, it's in a strong working condition. But for the NMOS, you are using NMOS to pull up, but NMOS is good at pulling down, it's weak at pulling up. So the size of 2 NMOS is actually works as a size of 1 NMOS normally, because it's in weak condition, like the resistance of it should be doubled. Like for the size of 2 NMOS, the resistance is 1/2 R equivalent N. But if it's a double, it's a kind of 1/2 times 2, that is 1 NMOS. So the actual strength of this NMOS is equivalent to size of 1 NMOS works normally. So that's why this resistance, the value of this resistance is equal to 1 times R equivalent N. because it works weak in weak condition. And for the bottom one, it's a size of 2 PMOS and works normally. The size of 2 PMOS, if we normalize it to be NMOS, is equivalent to size of 1 NMOS in driving strength perspective. So that the bottom one resistance is also 1 are equivalent N. So that's all the resistance in the path. So we calculate R total in the path. That is equal to 1 over 2 R plus 1 in parallel with 1. That is another half. That is equal to 1. So which means in the whole path, the total resistance is just a 1 equivalent to N, so that the reference inverter, the NMOS of the reference inverter should be 1, because in that case, they have the same driving strength, and the PMOS should be a size of 2. So then this is the reference inverter of our compound gate here. Then we can calculate the logic effort up. The J up is equal to C in gate over C in reference inverter. And C in gate is 4 plus 2. That is 6. And C in inverter is 1 plus 2. That is 3. So that the logic effort of this compound gate is just 2. And the next part is about the parasitic delay. So parasitic delay is about the contribution of the parasitic capacitance to the total delay. So in this case, you have 2 parts of the parasitic delay. It's not 1 part, because we have a compound gate. Now we have an intermediate node at here. So if we cause the node to be F, here this node to be out. Basically, this node F, it has some capacitance, internal capacitance, parasitic capacitance, because of the junction. Like the drain of this NMOS, this PMOS, this NMOS, and the drain source drain of the transmission gate that makes node F has some capacitance. So that the first stage, like the inverter, like if you regard this as a resistor, it will charge this node F capacitor first, and then charge the output capacitor afterwards. So there are 2 parts of the delay. That's because of the parasitic capacitance. Similarly, for the parasitic delay, it's also 2 parts. One is the output parts, the other is node F. So output parts is just as what we calculated before. That is equal to C parasitic output capacitance over C parasitic reference inverter. Because from the beginning VDD to the output, the reference inverter is this one. That is referring to the driving strength from the VDD to output. So this P out, the parasitic delay for output, the reference inverter should be the same as this one. So that C parasitic out is 2 plus 2, the 2 junction capacitance here. And divided by the parasitic capacitance of the reference inverter, that's 2 plus 1. That's 4 over 3. That's the first part of the parasitic delay. And the second part comes from node F, from the intermediate node. Similarly, still like C parasitic of node F over the C parasitic of another reference inverter, the reference inverter for node F. So basically for node F, you only use this inverter to charge the output. So for node F, the reference inverter should be this one instead of this one. Because for this one is the driving strength from the VDD to output. But if we calculate the delay for node F, the reference inverter should be this one because you use this to charge the output. So the inverter prime, that should be 4 to 2 inverter. So that the C parasitic of node F is 4 plus 2 plus 2 plus 2. That's the total junction classes here. Divided by the reference inverter's parasitic classes. So that is 4 plus 2. So add these two together is a parasitic delay. So this part is 10/6. That's 4/3 plus 3/6. 5. That is equal to 6. So for this compound gate, the parasitic delay is just 3, and logic effort is 1. So everything can be calculated, not just by guessing. And you also need to consider the pulling down logic effort in a similar method, and then find the worst case. So this is a way to consider the delay when you have a PTL, the transmission gate.